Am I audible to? Hope I am audible to everyone.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. I was talking that. Do you have any problem regarding the last classes? Because I have just discussed the deletion in a binary search tree in the last class. Also, how to construct the binary search tree. Do you have any problem regarding the binary search tree? Because we have already covered this topic. Do you have any problem? Any doubt? Any question?
No, sir.
Is it clear? Have you gone through the class note also? Okay. Okay, today we are going to discuss the another kind of tree that is called height balance tree. That is name is AVL tree. So before that, we want to know that what is the disadvantage of binary search tree. So let me draw a binary search tree so that you can get the idea. For example, one of the keys, for example, 50. Some key has been given to you, for example, 10, 15, 25, 35. Okay. Anybody can help me how to construct this binary search tree from this given key? Let me take more one also. For example, if I take 3, okay. What is the first node?
50, sir.
Right. Then 10 will be placed in the left hand side or right hand side?
Left, sir.
Left side, right. Then 15,
Then 15, sir. 10 right.
15 is 10 right.
10 right, sir.
Okay, good. 25,
25, sir. 15 right.
okay. 35,
35, sir. 25 right, sir.
okay. Make it 80 also. 80, 70, for example, 60. Okay. Then 3,
3, sir. 10 left.
10 left. Very good. Next 80.
80, sir. Right এ যাবে হ্যাঁ
Okay. 70.
70, sir. 70, sir. Left এ যাবে 80 left এ যাবে
Okay. 8, 60.
60, sir. 70 left এ যাবে
70 left. So this one. Please do not cross each other. Okay. Since I have just already gone through the picture, so I am not going to remember. So this is the binary search tree. If I construct from the same key, and if I want to change the order of this key, for example, if I write uh, 3 here, then make it 10, then 15, then 25, then 35. Okay. After that, if I consider 60, 50 is there. So if I write 50, if I write 60, then 70, what will happen? So 10 is the 3 is the first node, right?
3, sir. তোমার
10 is the second node, right? 15, then 25, then 35. Yes or no? And at last we
yes,
will
sir.
get, similarly we can get 50 after that. Okay, after that I will get 50, then 60, then 70. Yes or no?
yes, sir.
If I change the order, 70 first, then what will happen? Oh, 80 is also there. So last note is 80. Okay, so last note is 80. And if I change the order, for example, 80 is the first note, so I will get left heavy, right? 80 is the first note, then 70. In this way we will get 3. Yes or no?
Yes, sir.
Yes. Okay. If I change 25 is the root node, consider 25. If I exchange here, then there we will get different kind of picture. Yes or no?
হ্যাঁ
20
স্যার
is the root node, then 3 is the left, 10 is the, if I compare with this one, 10 is the right, 15 is the right, like this I will get different kind of picture. So I want to say that if I consider make it simple, if I consider some same key, for example, if I consider 30, then sorry, go to the previous one. So try to understand what is the height of this tree. Anybody can say what is the height of this tree? What is the height of this particular tree? This one, black one. If I the height of the tree, if I start from 0, then height 0. This is 1. This is 2, and this is 3. Okay. If I consider this in this way, the furthest most leaf is the height of the entire tree. So this is 0, 1. This is 2. This is 3, and this is 4. Height of the tree is 4. Okay. So, and if I consider this one, what is the height of the tree? How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So height of the tree is 9. Yes or no? If I
9,
count,
sir. Yes, sir.
if I start from 1, then if I counting in this way, the height of the tree is 9. But here, the same number of key, the height of the tree is less. So in this case, we can say that minimum height of a tree. So if I consider in this way that,
স্যার
yeah,
স্যার সম্রাট স্যার পেন্টিং আছে
okay, make it simple. So try to understand here. So if I want to reduce the height, here the maximum number height is of this binary search tree. This is binary search tree. You know that every key is, or whatever the key in the right hand side compared to the root is greater than, and in this way whatever the value in the left hand side that is less than to the root 50. So it's a binary search tree. So sometimes you are getting height is log n. Okay, it is not log n. So minimum height of this binary search tree is log n, and maximum, what is the maximum height? That is n. Yes or no? In worst case, the height
Yes,
of
sir.
the tree in this diagram is n, this diagram is n, but here if I consider in this way, so we will get, if all the nodes are if I take this type of example. For example, if I take this one, for example, the key is, for example, 30, then if I consider 40, then 10, 50, 20, 35. Okay, so how many keys there? 1, 2, 3, 4, 5, 6. Okay, make it 30 first, then 40. Okay, whether I am right or wrong, please inform me. 20 in the left hand side, then 50 is the right hand side, uh, uh, then 20 in the right hand side. If I consider 5 here also, so 5 in the left hand side, just I am making a tree which is login. Okay, and if I consider 35, so 35, 40, 35. Okay, and if I, this is the height, what is the height of this tree? This is the minimum height. Okay, log n, because this is a complete binary tree. So height log n. Yes or no? Height of the tree is log n. But if I consider this tree, and if I consider 50 is the first node, if I consider in descending order, then we will get 50, then 35. If I rearrange this key value, 35, then sorry, 50, then 40, then 35. So here 35, then 30, then 20, 20, then 10. So here the height of this tree is n. So what is the minimum height? Log n. What is the maximum height is possible in the binary search tree? That is n.
N, sir.
Right? So look at this. I want to say that same number of key, same number of key. How many numbers? 6 number of key. 1, 2, 3, 4, 5, 6, 7. 7 number of key, and another 7 number of keys. Number of key are same, but we are getting different type of height of tree. Why? Because if the order of the key or insertion of the into binary search tree, then order is different. If the key order is different, then we are getting, or we are constructing a binary search tree, the height will be different. Yes or no? Make it more simple. If I consider the three, for example, 10, 20, 30, 3 nodes. I am considering 3 nodes. Why I am considering 3 nodes, I will discuss. I will come to this point while a minute. uh, try to understand. So if I consider 10, then what will happen? 10, 20, then 30. Okay. Now if I make a tree, for example, 20, then 10, then 30, I don't know, I am just writing randomly. Okay. So what is the combination? 20 is my root node, left is 10, and 30 is my right hand side. Make it 20, 30, 10. What will happen? So I will get the 20, then 30 is the right hand side, and 10 is the left hand side. Yes or no? Okay. And if I change this 10, make it 10, then 30, then 20. Okay. 10 is my root node, then 30 in the right hand side. If I want to insert 20, it will be left hand side of 30. Yes or no? Yes or no? Am I audible to everyone?
Yes, sir.
Okay. So this,
Yes, sir.
this if I make different one, for example, if I make this one 20, then okay, make it 30, then I will get this one 10, 20. Yes or no? So 30 is my root node. Okay. This is 10, this is uh, 30, this is 20. Okay. 30, 10, and right child of the 10 is 20. Okay. Is it understood, this one? So look at this, we are getting different kind of, with the same key value, we are getting different kind of tree. If I construct, the order is different, then we are getting the
Yes, sir.
different tree. Yeah.
বলছি যে পরীক্ষার সময় কি রুট নোট কোনটা সেটা কি স্পেসিফিক ভাবে দেওয়া থাকবে না আমরা যেটা প্রথম থাকবে সেটা কি করব?
Which one is the first one? The first note will be, if nothing is mentioned, every time nothing will be mentioned in your exam, so first note will be treated as a root note. Every time the first node will be treated as a root node, right? Have you got the answer? Shanti,
हाँ सर बोलून सर.
who is asking this question?
नो सर
হ্যাঁ
সম্রাট.
হ্যাঁ সে বুঝেছি স্যার।
Okay, Samrat. Okay, sorry, Samrat. Actually, I have not seen the name. Okay, so here the first node will be, every time will be the root node. Okay, so every time this one is, in this case this is root node. Here this is root node. Here this is also root node. Root node. This this one is root node. Every time the first node will be treated as a root node. Okay, now come to the point what I am discussing here, that here the key value are same, key value are same, and number of key is also same, but the order of the key which I have just shown here is different. Okay, from that we can get that the height of this tree is 1, 2, 3. If I consider 1, if I consider 0, then 0, 1, 2, height of the tree is 2. And if I consider this one, what is the height of this tree? This is height 1. And if I consider this one, the height of the tree is 1, 0, 1, 2. Okay, and if I consider this one, this is height is 0, 1. Okay, and if I counting from 1, then it will be plus 1 to every of the tree. So you can consider 1, 2, 3, whatever it is. Try to understand, somewhere we are getting the height of the tree is less compared to the other one. Is it true? This conclusion is true. Some tree we are getting height, I just told you that Minimum height of a binary search tree is log n and maximum height of a binary search tree is n. Yes or no? I am not getting response from everybody. Is it understood by everyone?
স্যার এটা একটু আরেকবার বলবেন?
Which one?
এই যেটা এক্ষুনি বললেন।
Height of the binary search tree. For example, here we are getting the log n. We have just discussed two, three example in the previous example. And here height of the tree is n. Yes or no? Why it is
ইয়েস স্যার।
different? Because the order of the insertion is different. And now question is, here the number of keys, how many keys there? 3. So
3 স্যার।
how many possible combination is possible? 3 factorial. So if number of keys is
হুম।
3, then how many type of binary search tree we can draw? 6. Factorial of 3 is
6
6.
স্যার।
If the number of keys is 10, number of keys is 10, then 10 factorial combination tree are possible. Okay, where we will get different kind of height of each of the tree, right? So minimum height is log n, maximum height is n.
n।
Now come to the point. So why we use the binary search tree? Because searching is more faster compared to the other element. Yes or no? Searching is
ইয়েস স্যার।
faster in binary search tree, right? This conclusion. So suppose I want to find out 10 from this diagram. How many comparison is required? Anybody can say how many comparison is required? Suppose in this picture, I am going to find out this picture. I am talking about this picture. So make it. I am talking about this picture. So how many comparison required if I want to find a element? 10 is item or element or particular node, key value is 10, then how many comparison is required?
স্যার 1 স্যার।
No, not one. Try to understand. So first I will compare with first node, root node. This is my root node. Make it clear so that this was my 20, this is my 10, and this is my 30. Please everybody give the circle. Okay, for due to time I am just writing this key value only. Okay. Okay, if I want to 10, so this is first comparison. I will compare with the root whether it is less than or greater than. It is less than. Again come back to the
লেস
right
দেন
hand
স্যার।
side. Again another comparison. How many comparison is required?
2 স্যার।
2 comparison. But in case of this is 10, this is 20. Suppose uh, this is 30. So how many comparison is required? If I want to find out 10,
1
only one comparison. Make it different. For example, if I want to write my tree is like this, so many possible tree is possible. I told you how many comparison is required. One comparison. Then again we will compare with the root node. Two
3 স্যার।
comparison. Here three comparison. One comparison with the root node. Then second comparison here, and this is the third comparison. Yes or no?
হ্যাঁ স্যার।
Yes.
sir, yes, sir.
Three comparison is there. So since we are considering only three nodes, that we have seen that the comparison is different. Okay, number of comparison is different. Means searching time will be more or less. Okay, if the tree height of the tree is, this is the height of the tree is n, and for example this is log n, because this is log n. So log n. So if the height of the tree is log n, then number of comparison is less. If the height of the tree is n, then number of comparison is maximum. Yes or no? For example, in this tree I want to find out 30. So how many comparison is required? 3 comparison is required. If we consider this one 30, so 30, for example this value is 40, this 50, whatever it is. If I change the key value or whatever it is, number of comparison is different. Okay, in this example you can say that if I want to find out 10, if I compare with this one, so here the number of comparison is, since the height of this tree is n, here the number of comparison is much more compared to this one. Okay, since we are taking the value randomly, so that's why we are getting the conclusion randomly. Okay, is it okay to everyone?
Yes, sir.
Okay. So, uh,
Yes, sir.
so what is the problem with the binary search tree? Because what is the problem? Because if I change the order of the key, number of key is same and key value was also same, but if I change the order of key, we are getting the different kind of height of the binary tree. Yes or no? Sorry, binary search tree. We are
Yes,
getting
sir.
different kind of binary search tree. And if I want to perform the searching operation, if I want to particular find out a particular element, so the number of comparison will be different based on the tree structure. Okay, number of comparison will be different. Yes or no? We have seen that here two comparison, but in this picture we have seen that this is three comparison. So searching time is different. So we cannot control the height of the tree, or we can say that we cannot control how much time is required in the binary search tree. It is faster, we know that, compared to other one. So it is faster, searching procedure is faster, but we do not control which one will be the less, which one will be the last greater, okay, compared to this one. So what can I do? So if I want to improve the binary search tree in such a way that we can reduce the searching time of a binary search tree, so what will happen if this kind of tree, for example this one, if I consider this one, if I convert this tree into this tree, okay, if I convert this tree, then this tree, then the number of comparison will be less. Yes or no?
Yes, sir.
So
Number less হবে.
if I able to convert this tree into that kind of tree, so this one, so then number of comparison will be less. Yes or no? Everybody agree with me?
Yes, sir. Less হবে.
Let I want to response from everybody. Somebody just remain silent every time. Kaushik, is it okay?
Yes, sir.
Mahiddin, Mahiddin, Pritam, are you
Yes,
there?
sir. Yes, sir.
হ্যাঁ
Pritam,
স্যার আমি বুঝতে
Yes, sir.
পেরেছি।
Yes, sir.
Ritik.
Yes, sir.
Okay, okay. So if you don't understand, please stop me so that we can discuss more on this topic. If you don't understand, okay. Do not keep silent. Remain silent every time. Try to respond. So because it's an interactive class, we are just here to clear your doubt. So try to understand. Okay. Here we can say that what is the procedure by which we can change this type of binary search tree, we can improve this type of. So every time if I want to get that kind of tree, so we can change. For example, here just simplicity I am just discussing. If I remove, if I make this some note here, for example, if I make the 30 is the right child of 20, then we can get this type of picture. Yes or no? Okay, so this is called, actually, by performing some rotation we can improve the binary search tree into that kind of binary search tree where the height of the binary search tree is always log n. Height of the binary search tree is always minimum. Okay, so if I want to reduce the binary search tree height, then some rotation has to be performed. Okay, now come to the point. That's why we are going to use another kind of tree where the height of the tree is balanced every time. So that is called height balance tree, or that is called AVL tree. Okay, AVL tree. This is called AVL tree. So this AVL tree is named after the Russian mathematician. A is for addition, GM addition, V is for Velinsky, and L for EM Landis. So who discovered this item, this AVL tree, 1962. So this the name is come from three mathematician, Russian mathematician. So A is another mathematician, V is another mathematician, and L is another mathematician. So from three Russian mathematician give the name of the tree, that is called AVL tree. So AVL tree, or sometimes we call, is a height balance tree. So we have just discussed that whatever we have just discussed, we are going to improve the binary search tree into a height balance tree. So what is the definition of binary AVL tree? So first we have to understand that AVL tree is a binary search tree, or you can say it is a height balance tree. It's a binary search tree in which height of the left subtree and height of the right subtree of the root differ at most by 1. So what does it mean actually? The last point we have just mentioned. What is the height of the left subtree, height of the right subtree? Try to understand from here. So how can I calculate the height? That is called highest balance factor. So I will discuss what does mean the balance factor. First try to understand, that is called balance factor. Okay, if I want to find out the balance factor of height of left subtree, okay, H stands for height, H of left subtree minus height of right subtree, then I will get the balance factor. Okay, and the balance factor is maximum equal to 1. So what does it mean? It means that it may be maximum equal to 1 means it may be 1 plus 1, it may be 0 1, or it may be minus 1. So it means that maximum equal to 1 means this three value is possible, the balance factor. If this condition is satisfied, then we can say AVL tree. So before that we have to try to understand that how to calculate the find out the balance factor of a particular root node. Make it simple example. So please, for an example, this is 10, this is, for example, sorry, this is 20, this is 10, this is 30. So anybody can, what is the balance factor of this particular root node? I apply this formula. So height, no left subtree is possible, is present, no right subtree is present. So what is the left subtree? Height of this left subtree is 0, height of the right subtree is 0. So height of this root node, what is the value? What is the balance factor?
0, sir.
0. This one also, this
It
one
was
also
0.
0. So please try to understand, every time if the child node, the balance factor is 0, because left subtree right subtree is missing, so 0 minus 0 means 0, yes or no? So these are the leaf node, so this is 0. Now try to understand this one. What is the height of this tree, balance factor of this particular root node? 20. What is the balance factor?
2, sir.
Not 2. So this is 1 left subtree. How many left subtree is possible? So here
1.
only this is 1 and this is 1. Okay, so 1 minus 1, try to understand, this is 1. What is the left sub height of this left subtree?
अच्छा अच्छा 1 minus 1
1
0, sir.
minus 1, that is 2. Okay, if you don't understand, please go back to the previous discussion. Just I have just mentioned, I am just making it complete one so that you can get the idea. I'll make it simple. Try to understand. I am just taking the complex one so that you can get the clear idea how to calculate the balance factor of a particular root node. Make it large so that you can understand how to calculate the balance factor. Sorry, make it 2, not 20. Here this is the binary tree. No, it is not. I am just writing the node number, not key value. Okay, for understanding I am just writing the node number. Okay, this is node number 4, this is node number 5. I am just writing the node number, it's not key value. Okay, for node number 3. Okay, node number 6, for node number 6, 7, for node number 8. Okay, I'm just writing, this is not a key value. Okay, is it understood?
Okay, sir. Okay, sir.
This is not a key value, I'm just giving the node number. This is first node. So what is the balance factor of this node? This one, this is child node, this is
0, sir.
sorry, this is leaf node, this is leaf node, this is leaf node. So this is the balance factor is 0, this is 0,
0, sir.
this is 0, this is 0. We have seen just right now. Now what is the balance factor of this node? This is the left,
1
actually
minus
this is the left one. Okay, left one. What is the balance factor? So try to use this formula, because every time whatever we are going performing the AVL tree, how to construct the AVL tree, every time we have to rebalance this tree. Okay, so height of the left subtree minus height of the right subtree, right? So what is the height of the left subtree? That is 1. Yes or no?
One, sir.
How many paths?
One, sir.
1. What is the height of the right subtree?
Zero.
0. So right child is missing. So this is 1 minus 0 means plus 1. Yes or no?
Yes, sir.
If I consider this one, what is the height? If I consider this root node, suppose we are considering 2 is the root node. 2 is the root node.
1 - 1 হবে স্যার এটা।
Not 1 minus 1. This is 1. This is 2. 2 minus 1.
ও আচ্ছা আচ্ছা আচ্ছা।
Right, understood?
হ্যাঁ স্যার।
This is the left heavy. Okay, so this 1 1 2, so height of the left subtree is 2 and height of the right subtree is 1. So 2 minus 1 actually, 2 minus 1 is plus 1. Here 1 minus 1, make it change the color so that you can get the idea. Here 1 minus 0. Okay, here 2 minus 1. If I consider this one, try to understand, if this is 0, this is 0, so this is 0 minus 0.
জিরো
Answer
স্যার,
is
হ্যাঁ।
0. Okay, answer is 0. And now what is the height? This one, root node 1. Anybody can say?
3 - 2 স্যার।
3 minus 2, so that is plus 1, right?
ইয়েস স্যার।
So try to understand, in every time in this picture we get the maximum value is plus 1. Yes or no? We
হ্যাঁ
got
স্যার,
plus
+1।
1, we have not seen minus 1 here. So this tree is called balance tree. Okay, this tree is called balance tree, and according to this one, this is called balance tree. And make it another example so that you can get the different one. Okay, let me draw the another randomly. So for example, if I take 10, if I take 20, then 30, what will happen? So this is my 10, this is 20, this is for example 30. Okay, what is the height of this, what is the balance factor at particular node 30?
জিরো স্যার, জিরো।
Very good. So 0 minus 0, left light is missing 0. This one,
0 - 1।
right, this is minus 1. This one,
0 - 2 স্যার।
right, so minus 2. Okay,
-2।
if I consider 10, sorry, 30, then 20, then 10. Now wait, let me ask someone others. Pritam, am I audible to you? Pritam, are you
হ্যাঁ
there?
স্যার,
Just tell
বলুন
me,
বলুন স্যার।
what is the balance factor of this particular root at node,
0 স্যার, 0
this
স্যার।
one 10 at particular, this is 10, right? At root
হ্যাঁ স্যার।
root 10, this is 0. Okay,
হ্যাঁ স্যার, 0।
this one,
এটা স্যার 1 - 0 হবে, মানে +1।
this is plus 1. This one,
স্যার এটা স্যার 2 - 0 হবে স্যার।
so that is plus 2. Okay, so okay, so we have seen that we are getting the height of the tree. If I just consider in this example only 3 nodes, so we are getting that we are getting the height of a tree which is minus 2, which is plus 2, which is not in the range of the balance factor. Okay, I told you the maximum balance factor of a tree is
+1।
plus 1. Okay, so it may be 0, it may be minus 1, or it may be plus 1. So three possible value can be possible, and but here we have seen that here minus 2 plus 2 is the difference. Okay, so if this kind of tree, so what is the height of this tree is here the maximum, yes or no? Height of the tree is n, and here also
n
height
স্যার।
of the tree is also n. But what we are expecting? We are expecting to reduce the height of a binary search tree so that searching procedure will be faster. Yes or no? So we are always expecting to reduce the height of the tree so into a log n. So that means the searching will be possible. How can it possible? If I rotate some this one, if I rotate some, if I remove this one, if I use, this is called just like a chain pulley. If I pull down this node to here, so we can reduce the height. How? This is 0, this is 0, then balance factor is 0. Yes or no? Similarly, if I pull down in this order, this note, if I pull 30 note in the right hand of 20, then I will get the balance factor is 0, but the height of the tree is reduced. Yes or no? This is height 1, this is 2, but in this previous one the height was 3. Now it is height 2. Yes or no? Am I
Yes,
correct?
sir.
Yeah. So what is my expectation? But we want to reduce the height of the tree. Why? Because we want to reduce it. Since we were considering the only three note, later we will discuss why we are discussing the only three note. We will discuss. So we can get the minimum height of a binary search tree. So that minimum height of binary search tree is called AVL tree. And to convert that kind of tree, so for example this one, if I want to convert to this kind of tree, we need some rotation. So there are four type of rotation is possible, that is LL, LR, I will discuss later, okay, and RR and RL. Okay, this four rotation, what does it mean actually, and how to perform this rotation, whether it is single rotation or double rotation, we will come later. So before that, we make a conclude that what is the definition of AVL tree. So first, AVL tree is a binary search tree. First thing, is it clear? Is a binary search tree.
Yes, sir.
Second point is, in which the height of the left subtree and right subtree of the root, left subtree and right subtree of the root, each differ at most 1. So maximum balance factor, what will be the balance factor maximum? Plus 1, yes.
Plus one.
Minus 1, 0 and plus 1, not minus 2, okay. Minus 1, 0 and plus 1. So these three value can be possible, okay. Only these three value, not minus 2, not minus 3. This only three value is possible. So in which that definition, that properties is also applicable to the left and right subtree of the root are given in the AVL search tree. So AVL search tree or AVL tree is a binary search tree in which height of the left subtree and height of the right subtree of the root differ at most by 1, okay, and in which the left and right subtree of the root are again also an AVL tree. Understood?
Yes, sir.
Okay. So that is the definition. So how many things we have to know? We have to know the basic things. I have already sent the class note also. Please go through the last day class note. So here we can get the idea what is the time complexity, what is the disadvantage of binary search tree, and how can I improve the binary search tree. So like that, and what is the definition of AVL tree, how to calculate the height balance, the balance factor, BF balance factor of a binary tree from different example. Now we have seen that if I want to convert this tree to a height balance tree, then every time we have to perform some rotation. There are four kind of rotation. That is, one of the rotation is called LL rotation. Okay, LL rotation. Please remember this one, rotation. So then RR rotation, and LR rotation, and RL rotation. So how many rotation is required to perform? Only 4 rotation are required. Yes. So whenever we are
Yes.
going to insert any element into our generated AVL search tree, then we have to, if the after insertion, if the balance factor of this particular root node is different, if it is not 0, it is not -1, or it is not +1, then we will do some rotation. We perform some rotation so that the entire tree will be balanced. Okay, and always try to remember that whenever we are going to perform any rotation only, maybe is there are so many part of the number of node. For example, here there are so many node are possible in the entire tree, but rotation will be performed only on that three number of node, only this three number of node where we insert this node. Okay, so try to understand, this meaning is very clear to everyone. What does it mean the left L rotation? L stands for left and this L stands for left. So suppose considering one of the node is A, I am just giving the example. I'm just sorry, make it clear here. First I am discussing LR rotation, sorry, LL rotation. What is L? Suppose I am considering one of the node, this is for example A. Okay, the node is A, and the node value is for example 6. If I consider 6, and if I want to insert any node, for example 4, this is my new node. Okay, yes or no?
Yes, sir.
Now LL, what does it mean? LL, this is my previous, this is my existing node, and now this is my existing two node is present, AVL tree, and if I want to any node, that is for example if I want to 2. Okay, if I want to 2, what is the modified picture? That is 6, this is 4, and if I want to add it, whether it will be add in the right hand side or left hand side?
Left, sir.
Left hand side. Okay, now okay, so I will consider only these three nodes. That's why I have just mentioned A is the root node. What is the height balance factor of this root node at 4?
0, sir.
0. This one?
1 minus 0, sir.
So that is plus 1. Now what is
Plus
the
1,
balance
plus
factor here? What is the balance factor? This is 0, this is
0,
oh,
sir.
not 0,
Plus 1,
plus 1, this is,
plus 2.
so is it acceptable? So if I want to any
No,
node, where we have insert left subtree of left of the root node. Try to understand the meaning. Inserted node in the left subtree. L means, this is the picture actually. L means this is my root node A. Okay, so inserted node in the left subtree of, this is the left subtree, yes or no? Left subtree of node A. L means L for left subtree, then again left subtree. Understood? So LL rotation means inserted the node in the left subtree of node A. Have you got my point?
yes, sir.
Okay. If you make it, I will come later to understand the meaning. I am just inserting, for example, RR. If I consider the RR, so RR means I want to insert. I will discuss later. Right now, try to understand. For example, if I consider this is my 6, this is my 8. Okay, then if I want to insert any node, for example 10, so we can consider this one is a RR. So right subtree, so inserted node in the right subtree, inserted node in the right subtree, it is left subtree or right subtree? Right subtree, right of the node A, this is node A, right? And this
Yes,
10 is inserted right subtree, yes on, it is not left subtree, it is right subtree. So
right.
this is also right of the node A. Try to understand, and you will make it clear from this picture also. If I consider LR rotation, so what does it mean actually? LR means 3. If I consider this is 3, then 6, then if I insert R, uh, now the meaning is, I think now it is clear. So what is the meaning of LR? LR means inserted node in the right subtree. So where we have inserted this node in the right subtree. try to understand. This is LR, inserted node in the right subtree. Yes or no? Yes or no?
Yes, sir.
Of left subtree of root node A. Understood? So now I think it is clear now. This is right. So this right is for this root node. Okay. Okay, I have just inserted here. Right, right, this right, and left means left of A. A means this is the root node. Okay. Understood? LR
Yes,
means,
sir.
okay, this position. And if I consider RL, it will be very clear to understand that RL means what is the meaning of RL? I want to insert the tree node in the left of the right subtree of node A. Yes or no? So
Yes, sir.
so I will make it inserted left. Left means, for example, if I insert 7 here, so inserted node in the left. Yes or no? Left. So node is inserted is 7. Yes or no?
Yes, sir.
To the right subtree of A. This is node A if I considering this one. Understood? So what is the meaning of LR? LR means inserted node in the left subtree of A. RR means inserted node in the right subtree. This is the inserted node. Okay. Where we are inserting, and this position is identifying the where we are inserting. Okay, this one. So LL means inserting node in the left subtree of A. RR means inserting node in the right subtree of A. Inserting node in the right subtree of left subtree of A. And RL means inserting node in the left subtree of right subtree of A. Understood? This for notation. Meaning, what is the meaning of this rotation? Actually, what is the meaning of the rotation and how to perform the rotation I have just not discussed. How to perform this
স্যার ওই
rotation?
রাইট সাবট্রি লেফটে হবে।
Last one.
হ্যাঁ স্যার।
Which one is not understood by you? Last one.
ইয়েস স্যার।
Okay. Right subtree of L. Right subtree L means R stands for right subtree. Okay. Sorry, right of A. And L stands for we will start from this end. Okay. I will start from the right end. Okay. So left subtree of the inserted node. So initially, for example, if I consider this one, make it simple. Let me remove all those things. Make it simple. Okay, try to understand. This is my initial picture. This is 6, this is 8, and if I want to perform RL, RL means I am going to insert left. Understood? I am going to insert left. Okay, left. This meaning is clear. This is such a left. I am going to insert left. Left of what has been the right on? Right subtree of A. Okay.
ওকে স্যার, বুঝেছি।
Now it is understood. And LR, what does it mean the LR? LR means, for
লেফট
example,
লেফট সাবট্রি রাইট।
for example, this is 6, this is for example 3. This was my previous example. And if I want to insert any node, for example 5, then what will happen? This will be 6, this will be 3, and this is the next node which I am going to insert at 5. So this is LR. So inserted into right. Try to understand inserted into right of left subtree. This is the position of this root node. So left subtree of A. This is the left subtree. Left subtree, yes or no? Left subtree of A, but inserted into right one. Okay. So we will write in this way: the inserted into right subtree of left subtree of A. Like that. We can read in this way. I have not mentioned how to perform the rotation. Please try to understand this one. If I consider this one, I will discuss the how to convert one by one rotation. Before that, try to understand if I can find out the what is the balance factor of this node. What is the balance factor of this node? If I consider this three node, 6, 8, 7. What is the balance factor? What is the balance factor in this root node 7? Anybody can say what is the balance factor?
0, sir.
0. Very good. This one,
-1.
y minus 1. This is the left subtree,
Sorry, sir. Sorry. +1. +1.
plus 1. And this one,
Sir, -1 হবে।
y minus 1. No left subtree is present. No left subtree is present. So what will be the balance factor of this particular root node 6? 0 minus, this is 0, nothing is present here.
0
So height of the balance
minus
left subtree is 0, and height of the balance right subtree, what is the height? This one further slip node, that is the height. So height is, so 0 minus 2, so that is minus 2. So here the what is the definition of height balance tree? Because every time the at most balance factor should be plus 1, so here is minus 1, so we have to perform some rotation, yes or no? We have to perform some rotation, and how can I do that, we will discuss. But we here make sure that if I going to insert any node, the entire tree balance height of the balance tree is different, yes or no? That means that is increases, yes. Similarly, if I consider this one, this picture, this one, if I consider 6, 3 and 5, so here the balance factor is 0 minus 1, so that is this one 0, this is minus 1, and what is the balance factor is this one at root 6? Anybody can say? It is very easy, I have to discuss so many times. What is the balance factor? This is the left subtree,
uh,
this one, so this is plus 2.
+2. +2.
Okay, so this is also, I am not getting the right balance tree. Okay, we have just
Yes,
discussed
sir.
the
Yes.
maximum will be plus 1, yes or no? So whenever we are going to insert any node into binary search tree, so that we can get that, most of the time we will get not a balanced tree, so we will have to perform some rotation, and after this rotation we will see that the entire tree is balanced tree. So AVL tree is a high balanced tree, it's a binary search tree. And when we talking about the AVL tree definition, we will first mention it's a binary search tree in which the height balance of the left subtree and right subtree, that is the balance, actually if I consider this is the balance factor is at most 1, and in which left and right subtree also an AVL tree. Okay, so right, it means that it's a recursive definition. We know that all the tree definition are recursive definition. We have also discussed about the binary tree definition, binary search tree definition. So this AVL tree is also a recursive definition. Okay, so that up to this point is clear to everyone. I am just asking, then I will discuss how to perform the rotation actually.
হ্যাঁ স্যার বুঝেছি।
Okay, acha, same some basic things we have discussed. Then next day onwards we will discuss the rotation one by one. So today we will discuss the same thing, it's a AVL tree. So similarly we can say that in case of binary search tree, that we can represent by using linked list. So here also we can also represent by using linked list also. Okay, clear? Okay, now come to the point. I am just refreshing this concept. Let me run this slide. So first we will take binary search give the advantage of first search, but sometimes in few cases we are not able to get this advantage, because we have seen that in case of height of the binary search tree is sometimes is maximum, what is the height, is n. Okay, so we are not getting some advantage of for searching. So for example this one. Okay, similarly this one, so height of the tree is maximum, yes or no? Height of the tree is maximum, yes or no? I have just discussed so many times. Am I clearly audible to everyone?
Yes, sir. Yes.
So here the height of the tree is maximum too.
n sir maximum.
So that's why we will not get the advantage. Similarly here, if this kind of tree, so height will be maximum like that. So we will see the worst case such time for binary search tree in some cases when the height of the tree is maximum. Okay, so we will overcome this problem. That means we can improve the binary search in such a way that we can get the advantage of searching. So that tree is called balanced binary tree, are classified into two categories. Okay, one is called height balance tree, another is called weight balance tree. So here we are talking about the height. So that is called AVL tree or height balance tree right now. Okay, so height balance tree, a tree is called AVL tree or height balance tree if the node of the process one of the following properties. What is the properties? If the node is called left heavy, the longest path in the left subtree is longer than the longest on the right subtree, whatever it is, these are actually definition. So try to understand that AVL tree is a height balance tree. It's a binary search tree in which the height of the left subtree and height of the right subtree is at most 1. So that is actually called balance factor. Okay, so sorry, and if it is not, every time that we have seen that some of the cases where the root node is balance factor of the particular node is, for example, balance factor of particular node is +2, sometimes we get -2. Okay, so like that, if it is unbalanced, we have to perform some rotation so that we can convert this tree to into a equivalent binary search tree. Okay, a height balance tree. Okay, so this is called uh, okay, so this is unbalanced tree, these are actually balanced tree. So we will perform some rotation in some cases, critical unbalanced node to we can convert. It is clearly visible, the slide is visible to everyone what I am showing you.
Yes sir, visible.
Okay, sometimes tree becomes, because this thing is I have already discussed by handwritten note. Just I have just mentioned. So sometimes if I insert some nodes, that tree become unbalanced, and sometimes if I delete some node, the tree also become unbalanced. So then the based on the position where we insert, so based on the on this position, I have just mentioned that LR, RR, RL. Okay, so like that. So based on the position, we need to rotate the unbalanced tree. So the rotation is process to make the tree is balanced. So there are four kind of rotation. Okay, this is called right rotation, or I have just also discussed the one by one in next class also, all the rotation. And so 1 minute, হ্যাঁ বলো, হ্যাঁ 1 মিনিট, এটা একটু করি।